What I'm aiming to do is give an overview without too much detail of the range of activities that are going on in my research group at Warwick and in the broader collaborations that I'm involved in. First, a little bit of context about the two centres that I help to coordinate here at Warwick. The Warwick Centre for Predictive Modelling, so that's a university research centre that brings together expertise in scientific computing, mathematical modelling, and physical chemical modelling of challenging systems. And so this diagram over on the right shows you a little bit what the vision of this centre is. We're trying to bridge from the mathematical and computational sciences in the centre, where new techniques are developed, out to the application domain. In this context, particularly relevant engineering, physics, chemistry, materials science. And often we find that we need to adapt or expand algorithms that are developed in the mathematical sciences to make them applicable. So that's really the vision of this research centre, and it's a collaborative and interactive interdisciplinary centre. And then further to that, I'm involved in coordinating the HETSIS Centre for Doctoral Training. So this is a centre for training PhD students in a range of modelling techniques for tackling what we call heterogeneous systems, so challenging systems to model that involve more than one component, phase, material, etc. And a particular focus at the centre, and something that we'll get onto later in this talk as well, is quantifying uncertainty, especially across the scales. So if we think about materials and molecular modelling, we've got a range of techniques that we can use, from electronic structure up through atomistic modelling, mesoscale or microstructural modelling, and then continuum or finite element modelling to get close to parts that can be used in real applications. And at each scale in that hierarchy, different errors are introduced. And what we need to try and do as a community a bit more is assess and quantify those errors and how they affect quantities that we extract from one scale and pass up to a larger scale. So down at the bottom, an example could be the big unknown that we put in when we do a DFT, or density functional theory calculation, which is the exchange correlation functional. I'm not going to talk about that today, but there's been some work done in recent years to try to figure out what the extent of that uncertainty is and how it leads to errors in derived quantities. What I will come back to a bit later on is thinking about the next level up. So interatomic potentials, particularly data-driven or machine learning potentials, it's really important to think about what quantities they can capture and what they can't, and what error we might expect in something that we compute, which we would then feed in to a mesoscale, phase field, or finite element model at the larger scale. So that's the broader context. Zooming in a bit on my specific research group, what we're interested in my group is modeling what I call chemomechanical systems. So that's anything where there's both chemistry and mechanics active at the same time. Prominent examples include fracture, so crack propagation, there's bonds breaking, that's local chemistry. Friction, you're deforming a surface, rearranging bonds locally, but at the same time, both these processes are driven by a long-range stress field that is concentrating mechanical force down onto a nanoscale area. Similar challenges are found in oxides, in rocks. We want to extract minerals or metals from rocks with the minimum possible total energy cost. So understanding pressure processes is critical. And similar in metallic systems, we want to understand and control plasticity to give targeted mechanical performance of superalloy turbine blades, plasma-facing materials for nuclear reactors, or improved steels that are resistant to corrosion or hydrogen embrittlement. So these are the kinds of challenges. A brief overview of some of the work that's going on in my group at the moment and the people who are doing the work. Some of these projects we'll come back to later in the talk. Some of them I just want to mention briefly now. So Lakshmi is a PhD student in her final year working on modeling radiation damage in steels using interatomic potentials, machine learning potentials. We will say a bit more about that later on. Ian is also a final year PhD student. He's collaborating with the ICAM Center in Bochum and the OpenKIM project in the US, in Minnesota, to try to improve uncertainty estimates in interatomic potentials. And again, I've got a few slides that we'll come back to later on. Matt is working, sponsored by AWE, the Atomic Weapons Establishment in the UK, to further understand dislocation motion in tungsten, in particular, what happens when impurities like hydrogen or helium enter the mix. Tom is also a third-year PhD student, supported by Huawei, an optoelectronics communications company, looking at interactions between dislocations and defects, again with machine learning potentials. The NOMAD project that some of you may be aware of is a European Centre of Excellence on making best use of data that comes out of atomic scale and electronic structure calculations, and really trying to accelerate the performance of the codes that perform those calculations and make them ready for the exascale. There have been 2 postdocs working at Warwick as part of that project. Sasha Clowen, who's actually moved on now, is working for the FAIR-DI project in Berlin, and James Darby, and I'll talk a bit about both of their work later on. And then finally, a relatively new student, Fraser, has been working on fracture of amorphous carbon. I'm not going to say anything about that today, but there's really exciting future work coming there as well. So thinking about how we tackle these chemomechanical problems, as I sort of intimated in the introduction, we've got a range of techniques at our disposal, ranging from fully quantum, fully accurate things down at the bottom end of this hierarchy, up to more approximate, but more applicable approaches that can be used for very large systems. And if we want to understand something like fracture, the first idea would be to use something which is capable of describing a sufficiently large system that the boundary conditions don't overly determine the result. So we might think about using atomistic modeling into atomic potentials. We can, in principle, use a big enough system and long enough timescale. However, the challenge is getting sufficient accuracy to describe bond breaking or chemical processes. And until recently, this was very difficult to do with the previous generation of interatomic potentials. So if we look at fracture, we have a divergence in a stress field. We have the stress going as 1 over square root r as we get close to the crack tip. This creates a nonlinearity and a process zone where there's complex processes taking place. And while we can capture the stress concentration well with a simple potential, the kinetics or the dynamics of fracture tend to be very badly captured. So if we look in an experiment, we see an atomically sharp crack tip. This is an AFM. We see it's really very, very sharp, whereas in a simple simulation with classical interatomic potential, we massively overestimate the amount of energy that we have to feed in order to initiate fracture, and we lead to all this messy processes here, which are not correct and are not seen in an experiment because we're not describing bond breaking correctly. So the next idea might be to try to use a higher level of accuracy, to use something like density functional theory. It's a chemical approach that correctly describes many aspects of electron bonding, at least for a wide range of materials, but the challenge is it can't be used for very large systems. Now, depending on the quantities of interest, that could still be useful for many material science or engineering systems. If we think about fracture, it's a thermodynamic process. We've got energy flowing from some region that's stretched ahead of a crack tip through to the creation of open surfaces. And there is this Griffith idea going back nearly 100 years now that fracture is favorable when the energy that is released by unstraining a region exceeds the cost of creating these surfaces. So G is bigger than 2 gamma. And in principle, to calculate that, all we need is the elastic properties and surface energies. And that can be done directly with density functional theory in small model systems. This is some work we did a few years ago in silicon carbide in this direction. We had to be a bit careful here because we had to look at the right polymorph of silicon carbide. We had to think about different possible cleavage planes and different possible surface terminations. But if you take all that into account and calibrate carefully with very precise double cantilever experiments where cracks are stabilized for a very long time, so 400 seconds, the crack is growing only a few microns, and we look at the fracture energy that's required in different experimental samples, shown in red, and with the density functional theory direct calculations shown in blue, we get good agreements, much better agreement than with previous experiments, which are shown in green there, and just resynchronize a bit. Previous experiment shown in green. There we go. Get the laser pointer going again, which were not as carefully aligned and didn't correctly measure the single crystal fracture energy. So if we want to make a quantitative connection, and we can identify the relevant quantity and carry it out in a small periodic system, then DFT is fantastic. But it's very difficult for understanding the dynamics or the kinetics of these processes. And for that, I've worked quite a lot on combining approaches. So as was mentioned in the abstract in the introduction, concurrent multiscale modeling, where we describe a small part of the system with high precision, where we know that there is chemical processes taking place, and couple that with a more approximate description for a very large extended system. So we get the best of both worlds in some sense. We can describe big systems, long timescales, longer timescales. I'll come back to that in a minute. But we still retain sufficient accuracy when and where we need it. So if we return to the brittle fracture example that I showed earlier on, this is the same system, silicon cleaving on the 111 cleavage plane. If we look at what happens when we treat a couple of hundred atoms near to the crack tip with density functional theory, we now recover the mirror smooth fracture surface that's seen in experiment. And actually, it's even nicer than that. If we look carefully at the fracture surface, you see some reconstructions of the surface that are due to electronic effects. So we have an alternating chain of 5 and 7 membered rings here that's caused by delocalization of pi bonded electrons along this surface. So the DFT is really putting in extra information. We don't have to train or parameterize that on anything, and we can move to new systems rapidly. We can, for example, look at processes like stress corrosion. So this is where we have molecules from the environment, oxygen, water, etc., that causes cracks to grow at stresses which are insufficient for it to be energetically favorable on its own. We have to keep feeding with chemically aggressive agents in order to promote crack growth. And we can look at that by treating this small region again here with an accurate method like density functional theory, embedding it in a very large system like this. And we can describe as much chemical complexity as we like, providing it's localized and providing it can be described adequately with our quantum method of choice. This is a dynamical simulation, so we get temperature and free energy effects included automatically. But coming back to the hierarchy of models, the challenge here is that we're doing everything at the clock that is set by DFT. So the speed of the simulation is set by the cost of running a DFT calculation for every single time step or every few time steps. And that limits us to a few tens of picoseconds at most. We'll come back to how to lift that limitation a bit later on. But first, we need to think a little bit about what approximations we're making when we do this kind of concurrent coupled simulation. The big one is that we have to choose which region we teach with high precision and how we decide where to do that. What we'd like to do is for the entire system to behave as if we were modeling it with a high precision method, and so that we would get the same observables or the same average dynamics as if we were to do everything with quantum mechanics. For that to be true, we need what's called strong locality. So all derivatives of observables like forces have to vanish as atoms get far away from one another. That's true in many systems, but not always. If you have long-range electrostatic charge transfer, you may not be able to do this, for example. In metals and in covalently bonded materials, it's usually quite applicable. And then, as I say, we need to think about where to put quantum mechanical regions. The example I showed you, it was quite obvious where that should be. We know that there is a nonlinearity close to crack tips. The same thing applies if we're interested in plasticity and dislocation cause. We have a good idea in advance where we need high precision. That's not always the case. So if we look at another example here, this is a graphene nanotube polymer nanotube composite. So what we're interested in here is the mechanical properties of the combined system that consists of nanotubes and molecules. What we want to do is see how hard you have to pull in order to remove the nanotube from this system. And there are many points of contact between the polymer matrix and the nanotube in this case. And it would be very expensive to model the entire system accurately in order to capture those bond breaking events. So what we did in this case was have many small quantum regions centered on all of the bonds joining the polymer matrix with the nanotube. And actually, we were able to validate that very nicely in this case. So we did a one-off, very large calculation with an approximate quantum mechanical method, with a type binding method, density functional type binding. We looked at the stress strain curve, essentially, how much we strain and how hard you have to pull in order to remove the nanotube. And then we did the same thing with the classical model alone. You have to pull much harder, as in the simulation I showed earlier on. The classical model overestimates the energy required to break bonds significantly. Whereas if we use this coupled quantum mechanical, molecular mechanical approach, where we treat just these interaction points with quantum mechanics, we vastly reduce the overall cost and we get the same, more or less, overall response. There are some nice new algorithms coming out of collaborations with applied mathematics that can automatically determine for a given budget where best to put the high precision. So using error metrics based on geometry and information coming from interatomic potentials, we can identify what accuracy will be achieved with a given choice of quantum mechanical region, and grow it within some budget according to meet required constraints. So I think that's a nice emerging approach. One more example application on this front. This is work from a former PhD student who's just finished recently in my group, James Brixey, looking at interactions between cracks and defects. So this is in diamond rather than silicon. Now we have a diamond matrix, and the relevant defect is nitrogen impurities. So let's look first at the pure diamond case at the top. So we're looking here at fracture of diamond on the 1-1-1 plane. We see, similar to silicon, bonds breaking one by one, and the crack is propagating forwards. No reconstruction of the fracture surface in this case, so it's a simpler process. Bonds are breaking, crack is moving forward. If we add a nitrogen impurity, so the black atom here is nitrogen, within a quantum mechanical region, we can add these chemical impurities without any refitting or reparameterization. We now see that the crack interacts with the impurity and stumbles and effectively takes a step up in this direction, in the 1-1-1 direction, by one atomic plane. And that's a nice observation done at the nanoscale, but it actually turns out that it has macroscopically observable consequences. So if we look at some experiments, in the upper case where there are hardly any defects, we see a few features on the fracture surface, but not too many. Whereas if we look at a specimen which contains significantly more nitrogen, 400 parts per million, we see a real forest of these ridges on the fracture surface. So here, this is the crack propagation direction, cracks are moving forward. And the hypothesis is that these little triangular features correspond to individual steps where cracks are interacting with defects and stepping up out of the fracture plane. And actually, we can confirm that with a simple mesoscale model that's informed by the atomistic simulations. We can put in the required concentration of defects, and we see models of the emerging fracture surface that are in good agreement with what's observed experimentally. So it gives us confidence that this mechanism could explain the emerging fracture surface here. So this is a good example of what we can do with QMMM. It's nice that we can put in impurities, we can put in defects, but we are limited in the duration of the simulations. So these are quite expensive DFT simulations. They can only run for a few picoseconds. What I want to move on now is something that lifts another limitation of this approach. So here you can see we're looking at quite narrow periodic systems in the plane in or out of the screen that you're looking at. It's a quasi two-dimensional setup. It's periodic along that line. How can we lift that limitation while still keeping things affordable? And this is work done by a former postdoc at Warwick, Petr Grigorev, who's now in Marseille at the CNAM Research Institute. And the idea here is to take the setup that I've shown you so far, so a two-dimensional sort of cylindrical setup. Now we're interested in a dislocation rather than a crack, so a different kind of line defect in a material. And with a QMM type approach, we can correctly recover the core structure in the region of the dislocation. We can correctly describe dislocation glide, the motion of the dislocation in a glide direction. But we're limited in that this is a narrow periodic simulation, so the dislocation is forced to be straight. Whereas in reality, we know that dislocations move through the formation and growth of kinks. So how could we lift that limitation? Well, the approach that Petr came up with is to do what we call QMML. So quantum mechanics in the middle. The outside here is a machine learning potential. It's a relatively simple potential because all it has to do is capture the correct elastic response. Any complicated defects will be described within the quantum mechanical region. We used a linear machine learning model, and you can read more details in the paper that's referenced below. But the innovation in what we did really was to update or retrain the potential so that it is actually capable of fully describing the dislocation line away from further defects. So we did a few simulations like this with QMMM, and we improved our interatomic potential so that we could have dislocation lines described correctly by the interatomic potential. And then we could look at further effects. We could put additional defects, vacancies, or hydrogen or helium impurities close to the dislocation line and study that additional chemistry with localized quantum mechanical precision while using an interatomic potential for the rest of the dislocation line. So how did we do that? In a bit more detail, it was, as I say, a constrained retraining of the machine learning potential. And we did that using 3 different ingredients. We had the glide barrier for the dislocation that was measured using the fully quantum mechanical stroke machine learning approach, so the multiscale coupled approach with the short 2D dislocation simulations. We wanted to make sure we still had good behavior on the molecular dynamics. So we put in some configurations that ensured that we essentially regularized the constrained refitting. So we put in some high temperature and some low temperature bulk MD configurations. And then we had some really hard constraints that in order for QMMM to work well, you need to make sure that you have really good elastic matching between the quantum region in the middle and the classical region outside. Otherwise, you might get reflection of phonons from that interface. So there's a hard constraint that exactly preserves the energy volume curve, the elastic properties, so that we don't reduce the quality of that elastic matching. So putting those three ingredients together and looking at a couple of different dislocations, you can see we move from the original potential in orange to the updated potential that really matches very well with the quantum mechanical targets for both of these dislocation glide processes. And that's great because it means we can then move to a three-dimensional setting. We can go from this 2D case where we're a bit artificially modeling, if we put a defect in, a whole long line of defects interacting across the periodic boundaries. And it had been reported that this leads to a change in the dislocation core structure. When you add helium, in this case, into the core, so you move from one of these upward pointing easy core configurations to a downward pointing triangle, a hard core configuration. But actually, if you study the more realistic case of a three-dimensional simulation cell far away from where the helium is, of course, the dislocation line stays as it was before, and it's sufficient to treat that with our updated QMML model. Close to the dislocation line, we do see some changes. It doesn't actually go all the way to the hardcore because of being constrained by the rest of the dislocation line, and we instead see an intermediate split core configuration. What Vector was then able to do was put in more and more helium into the dislocation cores and look at the effects that has, and effectively extract rules that could then be used to inform larger scale simulations. So looking how different temperatures, energy barriers are changing and what that means for the resulting helium concentration. So it can really make useful predictions at larger scales. And the final thing that I want to mention here that's quite nice is that we looked at interaction between vacancies and dislocation cores. So there we don't need additional chemistry. So in principle, the machine learning potential should be sufficient to capture the interaction. And actually that works out pretty well. So let me talk you through this. The original potential is shown in blue. So you can see it's matching with the reference results shown with the blue squares quite well here. But down here where the dislocation and the vacancy are very close together, there's a significant disagreement between the original machine learning potential and the reference results that we got when we used quantum mechanics. However, if we update the potential, we do this refitting of the potential, we get the orange points here, and you can see that that matches very well with the reference result. So if we wanted to study more different configurations, do more compositional or structural averaging, we'd be able to do that just with the potential, which would be very much faster. So I think this is quite a nice way of combining simultaneous coupling to build training sets to update machine learning potentials with hierarchical passing of information from one scale up to another scale to improve a potential with information from the scale down. And then the example I showed with helium concentration provides a way to get up to very much longer timescales. So you could take out energy barriers or rates from these kind of calculations and use them to do something like kinetic Monte Carlo or exact analytical calculations, either using data from the interatomic potential or DFT data directly, or DFT quality data from an accurate potential to get up to very much longer timescales. So I think this is a nice combination of approaches. Now, I haven't said that much about how we do this, about how these machine learning potentials are informed by DFT data. So I want to dig into that a little bit more and show a few examples of recent work on that in my group. In particular, we've been using the GAP, the Gaussian approximation potential approaches. You can see there's a message in the chat, so I'm just going to, okay, it's fine. It's just a general message. The Gaussian approximation potential, but all of these potentials are similar in that the common assumption that we make is that we can decompose the total energy into a sum over contributions from individual atomic sites. In GAP, the way that we do that is in particular by comparing the atom of interest, where we'd like to make a prediction, with a set of reference atomic environments. through some kind of covariance kernel, and then we have some weights here that we've determined from our training set, essentially. So that's the Gaussian approximation potential or gap approach. This covariance kernel is typically based on the SOAP, the smooth overlap of atomic positions, and that's quite a well-established and successful technique now. There's actually just very recently a nice article about the capabilities of the gap code. Can't get the pointer right down to the bottom. The last reference from Sasha Kloen et al. On the archive goes into that in a bit more detail, and the earlier papers from Albert and co-workers fill in some of the background if you're interested. To show one relatively recent result from my group using this approach, and this is work by Harry Tunstall, who's a PhD student who finished a few months ago, looking again at silicon carbide, but now we're interested in the amorphous phase of silicon carbide. And what we want to reproduce is experimental observations of the radial distribution function, the structure of the amorphous, essentially. You can see the experiment of the black dashed line here. And what we were able to do is move towards an improved description of that. So let me go step by step. The first thing we do is try to match DFT. So black here is our reference DFT quench. We can only do that very quickly. It's expensive to take a liquid and to cool it down directly with density functional theory, so we have to cool it very fast. If we quench our gap at the same speed, at high speed, in blue, we can see it matches reasonably well with what you get if you do this very rapid quench. But that's not very realistic. It doesn't really match what's done in experiments where the liquid is cooled much more slowly. And the advantage of having an interatomic potential like a gap is that you can then go and use a bigger system and a longer timescale and do that quench more slowly. And when we do that, we get the orange result, where for the first peak of the radial distribution function, at least, we're starting to get better agreement with experiment. But there's still a bit to understand here. And our current hypothesis is that this experiment isn't showing a single structure. It's averaged over a few different structures. And that's why we're not yet getting comprehensive agreement with that. One of the challenges of these kinds of methods is accurately describing the environment, and a limitation of SOAP, of the smooth overlap of atomic positions, is that it doesn't fully do that. So it's only complete up to free body interactions, and you may want to go to higher body orders in order to more accurately describe the environment. And one successful way of doing that is with the atomic cluster expansion approach, ACE, introduced by Ralph Droughts a few years ago, which actually can be used in quite a simple linear setting. So the idea then is that your atomic energies that go into this total energy formula just come from a dot product of some coefficients, which you learn from data, and some basis functions. And there's a recipe for constructing these basis functions in such a way that they're invariant to all the required symmetries, translation, permutation, rotation, and that you can make them complete up to a desired body order. So 3 body, 4 body, 5 body, whatever your desired accuracy is, you get more and more basis functions the higher body order you go to, and hence more coefficients and a more flexible model. And recently, in this first paper at the bottom by Chuck Witt and et al. That's just come out this week in JChemVis, we've refit a silicon gap model that was very general, that was published a few years ago with this ACE approach, and get generally comparable performance across the board. So this is the accuracy on point defects, elastic properties, surface energies. It's in general pretty much as good as the gap, and quite a bit cheaper because this is a linear system here. So if I return to the fracture example, if I take that ACE model and apply it to the fracture of silicon that I showed you earlier on, that's actually quite well described on this model. We see the same surface reconstruction that I showed you before, the alternating pentagons and heptagons. So we're capturing electronic structure effects within the model without having to include them explicitly, and we're getting a good description of fracture process. This was a quasi-static simulation rather than the molecular dynamics one I showed earlier on, and that explains why it looks a little bit more jerky, but it's really doing a pretty good job. There are some remaining challenges though. These examples I've shown are only 1 or 2 chemical species. What if we want to model many more? Come on to that in a minute. What if we want to use very large training sets? So what if we can't fit our training database onto a single machine, and we want to use a very large training set? And then the last topic I think we'll have time to cover today is how can we improve accuracy of uncertainty quantification? So the first one is work by James Darby, who's a postdoc working with me at Warwick, who's done some really nice work together with Capocciani on thinking about how we can apply these models to systems that contain many, many different chemical species. And what James has proposed is extending this SOAP descriptor so that we have a part which is the same as before, which is sensitive to individual chemical elements. So we're comparing a density of one environment with the density of another after rotating, and then we're integrating out the rotations. So this part, if you're familiar with SOAP, is really the same as before. But then what James is adding is a part here which doesn't care about chemical species. So these labels alpha here are for chemical species. This part of the covariance kernel is agnostic to elements. And then we get to choose these powers here to choose the appropriate balance between the element sensitive part and the element agnostic part, essentially. So the traditional SOAP has nu equals 2 and mu is 0. It only has the element sensitive part, and that leads to a descriptor which scales quadratically, both with the number of chemical species, S, and with the size of the radial basis set, N. And by playing with these numbers, we can reduce that. So we can come down here to reduce to linear cost, or actually we can also compress in the radial direction, and that's represented in this picture by projecting onto unit sphere. So taking one of our neighbors, keeping both its chemical species information and its distance information, and for the other one, bringing it in so it lies on the unit sphere. We tried this out for a challenging database containing 5 different metal atoms as a high entropy ally data set. 1, 2, 3, 4, 5. Yeah, that's right. And this is based on some previously published work by Jesper Begermaster in Kai Nordlund's group, where they'd actually decided that the best approach was not to use a many-body descriptor at all, but to stick with a 2-body or 3-body descriptor, because it's very challenging without any compression to actually fit these models. And you can see that the full SOAP is saturating here at a limited accuracy. But with the compressed approaches, we can get down to higher accuracy, and we can keep improving as we increase the size of the basis set, essentially the number of sparse points that we include. This point here, you can see it stops smaller. That's actually because it's very challenging to fit these very large models, and that actually brings us on to the next point, which is work done by Sascha Kloen, a former postdoc at Warwick, who's actually moved now to Berlin to the Fermat project, which is to parallelize the way that we fit these Gaussian approximation potentials models. So what you do when you fit this kind of model is linear algebra. We're solving a linear system. It's a kernel ridge regression or sparse Gaussian process model, and we have to essentially solve a least squares system. So we end up with a big QR factorization of a matrix, and information about chemical and atomic environments has gone in to these matrices here. So the original way this was done was with a giant matrix A and a giant vector of observations B that contains all our energies and forces, and then we want to get out these coefficients C here. And what Sascha proposed is splitting that up into a series of independent matrices that can be distributed across a large machine, and then we can do that construction of these matrices and the linear solve and the solution of the least squares problem in parallel. And this actually works really well. It's really nice and scales up to several thousand cores. So this is work done within the Nomad project, and the code is now publicly available. It's merged and it's part of the QUIP GAP code. You can see it doesn't matter too much how you partition between MPI and OpenMP, so between threads and processes, providing you make a reasonable balance between the two, you can get really good scaling up to a few thousand cores and dramatically reduce the amount of memory that's required for the calculation. Most of that speed up is actually coming from descriptor and covariance evaluation. So by building these different parts of the matrix in parallel, we can trivially fill them in parallel, and that doesn't require any communication at all. So we get a big speed up moving through these dark shaded bars as we increase the number of cores. The speed up in the linear solve is smaller, and that will saturate at some point. So you can see that on average, that's only improving a little bit, but the overall speed up remains good. I now want to show one or two final examples. So the first one is a Gaussian approximation potential for a complicated 3-component iron, chrome, nickel system. And this is work of Lakshmi Shenoy in her PhD project here at Warwick. There's a few innovations here, but I think I'll focus on a particular one, which is about how we represent atomic environments, and in particular, how we deal with challenges in this system associated with coupling between spin degrees of freedom and structure. So we're interested in this 70% iron, 20% chrome, 10% nickel system. We can build model systems with the correct short-range ordering using effective medium theory. I'm not going to go into that in too much detail, but you can have a look at the preprint link below on the archive if you're interested. We can evaluate them with DFT, and we can build reference configurations to build a model. We're interested in this low temperature antiferromagnetic part of the response, where actually we get interesting distortion of the lattice. So we don't get a cubic lattice like you would at high temperatures and like you do in simpler materials. We have two lattice components equal and one longer direction associated with ordering of the spin in antiferromagnetic layers, up, down, up, down, up, down, along that long direction. And we struggled to describe this with a gap model initially when we were using a standard gap model with 3 species representing the 3 chemical species. And what Lakshmi has done very recently actually is to expand that a little bit. And we've taken a fairly sort of simple approximation where we're using 2 different species to represent the upspin and the downspin information. So we're not fully describing the magnetic response. We're describing it in an approximate way where we're saying half of the atoms are upspin and half of them are downspin. We're taking this information from the magnetic moments in the DFT calculation as additional input, but we're not fully describing the magnetic response. We're just categorizing it. So it's a categorical variable rather than a continuous variable describing the spin. But it really leads to a very big improvement, first of all, in the accuracy with which we describe the energies of the target configurations. So we're using the compressions that I described earlier on as well. And we can see that doesn't make too much difference in terms of accuracy. So we have the original gap model in blue. This is a cumulative distribution function. So it's showing you what the error is, what proportion of configurations have a given error. And we'd like it to be up here in the top corner. So you can see here we've got significant errors of up to a couple of millieV per atom on 5 or 10% of configurations, both with the gap and when we do this species compression, which makes it faster but doesn't significantly reduce the accuracy. However, when we move from these 2 guys to the green, we introduce this additional species that represents the different spins. We get a really big improvement in the accuracy. Same thing for the training configurations and for the test configurations over here on the right. But more importantly, we start to correctly describe this tetragonal distortion. So let me go through that. So if we look first of all at what we get from DFT, it does describe this one long direction nicely. So we have 2 shorter lattice constants and 1 longer lattice constant, and there's a distribution of values that you get because of the random ordering in the array in the alloy, but you get clear separation of these things. If we use a simple embedded atom model, it doesn't know anything about spin. It can't really describe this at all, and so it gives you a cubic structure with just 1 lattice constant. The original gap is sensitive to spin through the local structural deformation, but doesn't really know how to interpret it. Doesn't have information about the spin of particular atoms, and so can't really describe it properly. And so it gives you 3 different lattice constants, A, B, and C, all different. So an orthorhombic cell. But when we move to the spin gap that includes spin information, we really manage to correctly describe the FCT structure. So the 2 short lattice constants and the 1 longer one really nicely. And similarly, we can describe elastic properties. So energy volume curves come out nicely and are in good agreement with DFT calculations that include all the spin information. And we start to describe point defect energies more accurately as well. So we get an improvement in the description of the vacancy formation energy, for example. We can remove any kind of atom and we get the same distribution of formation energies, and they're starting to be in reasonable agreement with DFT. There's still a bit of a difference to understand there, and that brings me on to the last topic in the last 5 minutes or so of this talk, which is to think about uncertainties. So going back to what we did with the original silicon gap, an advantage of the gap or the Gaussian process framework in general is that, as well as a prediction of the mean of the result, you get a prediction of the variance of the accuracy of the calculation. That's done through the formulae shown here. But until recently, it wasn't really possible to make this very quantitative. So it was a sort of error indicator that's useful for things like active learning. But because it's mixing together different sources of uncertainty, it's mixing together contributions that are missing from the model with imprecise estimates of the parameters that we've got, it makes it hard to use as a real calibrated measure of uncertainty. And so it can't be used to put errors on properties like vacancy formation energies. So the last thing I want to tell you about is work done by Ian, who's finally a PhD student in my group as well, to use a method called conformal prediction to try and tackle this problem. And the way that conformal prediction works is that you take some score function, it doesn't actually matter what it is, but some way of saying how good is a particular measurement in terms of how far is it from the correct result and what is the associated error with that. And then you use those scores to calibrate your error estimates. And actually you get some formal guarantees that the results that you get will form prediction sets where the true result is guaranteed to lie within the interval given by a lower bound of the mean prediction minus some scaled uncertainty, and an upper bound on the other side. And there's a recipe to decide how much you need to scale the uncertainties in order to make this true. And you essentially tune this scale factor on a calibration set, and then you test that it works on more widely as well. So how do we apply that to interatomic potentials? We're using the ACE framework that I briefly mentioned earlier on. So we have a linear model, coefficients times basis functions. We assume some error, and we assume that that error is Gaussian, so it's random noise, essentially with some standard deviation or precision. We assume that we know our coefficients should be small and also have some unknown noise on them, some Gaussian noise on them. And then we find the values of these two precision parameters using a Bayesian scheme, essentially, so we maximize the evidence. And that gives us a way of sampling models, sampling different choices of models, all of which are compatible with the data that we've got. And from those models, we can form a committee that gives us both a mean prediction that we can use as our central estimate and a standard deviation across the members of that committee. And then we can use this conformal prediction idea to rescale those errors, so to compute these scores, which say how far away is a particular mean prediction from the true calibration result, and what's the associated error with that, and then use this rescale factor to scale up or scale down those uncertainties. And this actually is working pretty nicely. So these are some results Ian has got using this same silicon data set that I've shown a couple of times. So what we do here is we draw a series of different models, we can formalize them using this approach, and then we use them to get our estimates on quantities, in this case, the bulk modulus. So, oops. Sorry. I think the line appeared and disappeared very quickly. So what I'm showing here is a slice through this map here, where we use a constant amount of data, so 150 training configurations, and we vary the accuracy of the model, the complexity of the model. So we make our model more and more complicated. We use more and more basis functions, higher and higher maximum polynomial degree. And what we see is that the models improve, the accuracy, the mean accuracy matches to the target a little bit better as we go on, but also the error estimates improve. And what's really nice is because we've used this conformalization approach, all the error bars cover the true result. So the DFT result for the bulk modulus is shown here in blue, and actually not quite all, but most of the error bars are sufficiently large to cover the true result. We have 95% coverage here, which is why the last one doesn't quite cover. That's something that we can actually choose when we set up the approach. One more example of this. This is elastic constants. So if we use a low accuracy potential that's not got very many degrees of freedom, not a very complicated potential, and we increase the amount of training data, it doesn't really matter. It doesn't improve the model. The model isn't capable of describing the correct results, but the error bars correctly capture that. So these calibrated error bars show you that the predictions from your model are not very accurate, and they do cover the true result. If we make our model more accurate, we put more degrees of freedom into it, we then get into a data limited regime, where as we increase the amount of data, we get a step from models which are insufficient to models which are good enough, and where the error estimate is sufficiently accurate as well. Okay, I did include a few slides which I'm not going to have time to go through on the final topic of coarse graining from density functional theory to tight binding style models. So I think maybe I'll just show one picture on that just to show that it exists, and then I'll skip to the conclusions. So the idea here is to take a reference set of density functional theory calculations and use the Hamiltonian and overlap matrices from those calculations to build a model using a very similar scheme to what I've described. So using an ACE basis set, but expanded and generalized so it works with blocks of matrices rather than atomic environments. Still uses atomic environments to describe them, but the target values rather than energies and forces are now blocks of the Hamiltonian matrix. And we can use a similar setup to make predictions for on-site and off-site blocks of the Hamiltonian. And from that we can get, let me skip just to show one result from that. From that we can get very nice predictions of electronic structure. So now we're getting access to electronic quantities directly from these data-driven models, rather than just energies and forces like we have in interatomic potentials. So with that, I think I will conclude so that we do have some time for questions. I have just a few conclusion points. So multiscale approaches can help where you need localized precision. Machine learning potentials are now sufficiently well developed that they're really useful for materials science, for looking at complex processes like fracture, dislocation, motion, and we can start looking at more complex alloys, including ones where spin or magnetism are important. There are many opportunities for data-driven approaches on other scales as well. So I briefly mentioned tight binding models or tight binding style models, but there are many other scales where we could make use of these approaches as well. And I think we all, as a community, need a real focus on applying uncertainty quantification techniques to look at the unknown knowledge, the epistemic uncertainty in the predictions that we're making, as well as the random errors. And in order to do that, we need to get error bars, not just on energies and forces, but on properties. I've shown one way that we're starting to do that. Okay, so I think I'll finish there by acknowledging everybody who's contributed, particularly my group, but also collaborators elsewhere, funders and providers of high-performance computing resources. And thank you all for your attention.